Okay, let's start. Welcome to our second talk this morning. I'm honored to introduce Professor Liu Qieyan from Microsoft Research. He's a distinguished scientist there, and he's also an IEEE fellow, ACM fellow, and an AA fellow. He is also the adjunct professor at many universities, including CMU, Tsinghua, University of Science and Technology of China, etc. And also, as a researcher in an industrial lab, he make unique contributions to the world. And many of his technologies has been transformed into Microsoft products and online service, such as Bing, Windows, Xbox, etc. And over the years, Liu and his team has published numerous papers, hundreds of papers on top-tier conferences and journals. And he has also won many awards, including the most cited Chinese researcher, and China AI Leader Award, and the most influential scholar award, etc. Today, he will give us a talk on AI for molecular science. Let's welcome.
Thank you very much, Yuanfeng, for the introduction. And it's really my pleasure to be invited to ICBS to share our recent research on AI for science. And this topic is actually interdisciplinary research between artificial intelligence and natural science. I am an AI researcher working in Microsoft for over 20 years. I have witnessed the evolution of the entire space of AI in the past decades. It's quite interesting. As we can see, these days, AI really achieved significant progress in many dimensions. If you go to a typical search engine and input something like artificial intelligence, human parity, you will see a lot of results like these. And I'm quite proud Microsoft Research and also my own team contributed a lot to this process. And in the past 5 years, I think people's attention has been paid to those breakthroughs like the GPT series. And also, Microsoft and my team plays quite an important role in the collaboration with OpenAI, etc. But if we look at all this AI booming, somehow we will realize that most of the achievements are still centered around mimicking our own behaviors, like the speech, language, vision. And a question is whether these capabilities, basically they are basic fundamental capabilities of human being, are the key for us as human, as the most intelligent creature on the earth, to distinguish from other creatures. In my own opinion, the answer probably is not. It is not because we can speak, we can see, we can hear that we are different. Instead, we are so different because we have the capability and the courage to discover and transform the world around us. And this goes far beyond ourselves. For example, for this microscopic world where we cannot see, we cannot hear, but still there are a lot of things going on there. Right? And also for the infinite cosmos, most of us haven't really touched that in any chance, but there's those kind of things out of our imagination really defines where we are in the cosmos. So the question is, if we are human, we are special because we can understand, discover, and even change or transform the world, why we shouldn't really expect artificial intelligence to do the same thing? So this is why many researchers started to look into the space of AI for science. And science is really very interesting. I think this conference is ICBS. Basically, many participants are actually from the natural science or mathematics and physics background. This slide shows some very interesting scientific questions. This was proposed by the Science magazine to celebrate its 125th anniversary. And you can see there are really some very, very fundamental scientific questions. Defines who we are, where we're going to go. And they basically belong to biology, physics, and many other important disciplines. Not only this basic natural science, we also have scientific technologies which also help us interact with the world around us, like the drug discovery, like material discovery, weather forecasting. There are many talks in this conference covering these topics. Jim Gray, one of my former colleagues at Microsoft, once proposed a paradigm, kind of a category of paradigms to categorize how people do natural science. For example, the first paradigm is called empirical science. Basically, they can be traced back thousands of years ago. And second paradigm is called theoretical science. Some really brilliant scientists use scientific equations to summarize what they have observed empirically. But it is not really easy to solve those equations. So until the invention of a computer, before that, people can hardly solve complex equations. They can only do some toy examples. So the third paradigm is called computational science. People study to leverage digital computers to solve scientific equations to understand more about the world around us. And in the past decade, with the increasing size of the experimental data and also the faster development of machine learning and artificial intelligence, scientists started to use machine learning to analyze those massive data, try to find out some patterns or some interesting principles hidden in the data. So that is what we call data-driven or data-intensive scientific discovery. And in just the past 2 or 3 years, people have been very actively investigating in a new paradigm, which we call AI for science. So someone may have the question, what's the difference between AI for science and data-intensive scientific discovery? So basically, we believe the leverage of modern AI technologies, like deep learning, like foundation models, will be the key. And also the deep integration of those AI with theoretical science, like all those scientific equations using the simulators, emulators, and also the whole flywheel loop to empower the scientific discovery will also be the key. So that distinguish AI for science from the traditional data-driven scientific discovery. And today I'm going to talk about a special domain inside AI for science, which we call AI for molecular science. This is because, in the microscopic world, this molecular space, we have very good knowledge about what's going on. We know the underlying scientific equations, basically the Schrödinger's equation. If we can solve that, we will know everything, almost everything about the molecular system. For example, we can resolve this wave function. Based on that, we can predict the energy, forces, and other physical and chemical properties of the molecular system. And based on that, we can even simulate how those atoms inside a molecule will move around so that we can get this so-called molecular dynamics. If we can have all those things done, we will have a very deep understanding of the molecule. And molecule is a very basic unit of our world. However, if we look at the whole process, the tools people are widely using are something like those quantum chemistry tools, like density functional theory. Those tools are effective, but they are very, very slow, especially for very large molecular systems. So in recent years, researchers started to think about whether we can use artificial intelligence to accelerate this process. For example, instead to solve a kind of SCF loop, a kind of iterative process for DFT, can we use AI to provide end-to-end prediction from the, for example, atom coordinates inside a molecule to those molecular level properties like energy, force, conductivity, and others. If we can do that, we can significantly speed up the whole molecular dynamic simulation process and can really transform the molecular science. Talking about using AI to model molecules, actually a very natural choice is to use graph neural network. Let me explain why. Because molecule is basically a graph. If we regard each atom inside a molecule to be a node, and also model the, for example, chemical compound between different items inside the molecule to be the edge, then we easily can transform a molecule to a graph. And then if we can use graph neural network to do the message passing through the edges, to aggregate all the information, we can pretty much have a good modeling of the molecule. Actually, that is also many researchers have been doing. But on the other side, if we carefully look at all the previous work on using GNN, graph neural network, to solve molecular systems, we will find one problem with them. That is, graph neural networks also do not scale very well. If you look at all the published work on graph neural networks, they usually have a very limited number of layers. For example, 3 layers, 5 layers. While the transformer model has scaled to hundreds of billion primers, usually graph neural networks is small. And it cannot really learn from massive data and achieve the so-called scaling effect or the emerging capabilities. Although there are a few papers recently talking about the scaling effect of the graph neural network too, but if you look at those papers, I think the community hasn't come to any consensus whether graph neural networks can really scale. Then knowing the limitation of graph neural network, then the second choice is to borrow those scalable models like transformer to solve this molecular modeling problem. Actually, also, many people have already been doing so. But unfortunately, direct application of a transformer to this problem doesn't work either. Basically, this is what people have done. They encode the molecule using a sequence, like the SMILES sequence, and then directly input that into the transformer, just like a sequence modeling or language modeling, and train a model and use that model to predict different kinds of properties of our desire. But as I shown on the slides, unfortunately, on many benchmark datasets, such an approach achieves even worse results than the fine-tuned, well-tuned GNN model, even if the transformer is big. Then what's wrong here? So basically, looking at the situation in the research community, probably 2 or 3 years ago, my team had a very serious investigation into this problem. On the one hand, we believe transformer should work. On the other hand, we want to know what is the factor preventing transformer from working very well here. And to understand that, let's take a look at the self-attention module, which is a key component in transformer. Basically, it defines the relationship between different objects of our interests. And from this attention model, you can see that it is permutation invariant. Basically, it means that this attention module does not consider any position, structure, and also other order relationship. They actually just regard the objects as a set, ignore all the structure and the other higher order relationship inside that. But as we know, order or position or sequence or structure really plays a key role. For example, in a natural language sentence, different position of a word may really mean different meanings. And also in a 2D image, if you move around those pixels, basically you will get a different image. So position information or structure information really matters. And how a transformer deal with that? It is called structure encoding or positional encoding. If you know about transformer for NLP, you will know people have done a lot of work on the absolute or relative position encoding, and there are a lot of tricks. Then the question is, when we use transformer to model molecules, what is the appropriate positional encoding or structure encoding? If we can do that well, probably transformer will work in this case. So 3 years ago, my team did a very simple attempt. Basically, we introduced 3 different types of structure encoding. One is called topological encoding. The other one is importance encoding, and the third one is connectivity encoding, basically edge information encoding. And we also use some very simple realization of those encodings. For example, for topological encoding, we just use the shortest path length between items to represent that. For importance encoding, we just use the degree information of each item on the graph. And for the edge encoding, we just use the Gaussian kernel of the Euclidean distance between items for that purpose. By adding this structure encoding into transformer, basically we get a new model, which we call Graphormer. It is a transformer with some graph structure information. And we apply this new model Graphormer onto these molecular modeling tasks. We did a lot of experiments, especially we tested the scaling effect, whether this new model, transformer-based graph model, really has the desirable scaling effect. You can see this scaling law. We started from a small model like 100 million parameters, and then gradually increase the data set, increase the number of parameters up to 22 billion parameters, which is a really big model. And then we can see consistent improvement of the prediction power of the model. And also we test that model on terms of benchmark data sets, tasks. And this is just a subset of them. We achieve SOTA on almost every dimension of that benchmark evaluation. Also, we use this Graphormer model to participate in some competitions. One is, the early one is the first OGB-LSC challenge on large graph modeling, which is basically a molecular property prediction task. And then we attended the first open catalyst challenge also in 2021. In those two competitions, we obtained the first place, both really beating organizations like DeepMind, like Meta and others. And interestingly, for the second occurrence of this OGB-LSC challenge, we didn't participate by ourselves, but interestingly, if you look at the top 3 winners of that competition, they all leverage Graphormer or its variant as the backbone model. Basically, that shows how Graphormer can really solve the molecular task very well. And we also open source Graphormer. If you have an interest, you can go to GitHub, have a try. Graphormer has also been offered as a web service in Microsoft Azure computation platform. Several big pharmaceutical companies and chemical companies have leveraged that. And from what I heard from those customers, they have achieved some really significant improvement over the model they trained by themselves. Yeah, so that's the first story about how we can use or adapt an existing AI model to better suit these molecular prediction tasks and achieve some significant progress. Although Graphormer has led to some success, but as one of the authors, I know the limitation of Graphormer because its attention model still has a very high complexity, the quadratic complexity with respect to the number of items. It can perform very well for small molecules with, for example, 100 items inside. But if we want to use that model to deal with large molecules, like protein, like the whole virus, for example, there may be billions of items inside. In that cases, the attention model in transformer will become a huge bottleneck. So this is why we start to think about how can we further change the AI model to handle large molecules. A very simple and actually naive solution is to do some fragmentation. For example, if you have a large biomolecule, like a big protein, you can cut it into pieces, and for each small segment, you can apply models like a Graphormer to obtain some prediction on the local energy or some other properties. And then we can use some other tricks to integrate all the prediction results together to achieve the overall characterization of the large molecule. And this is not something new. This is actually an old story. For example, in the traditional field of classical molecular dynamics simulation, people also do the same thing. They do some local prediction and then use some formula like that to introduce some long-range effect back, like those van der Waals forces and other long-range forces. So what we have done is, for each segment, we use our AI model like a Graphormer. And for the integration, we just simply leverage those existing tricks in the field of molecular dynamics, classical molecular dynamics simulation. And it works pretty well. And furthermore, in addition to this fragmentation idea, we also think about what's the difference between a flexible molecule like protein as compared to some non-flexible molecule like small chemical compound. You know, for those flexible proteins, usually its parts can really move around, turn to different angles, and so that will lead to the so-called conformation change of the protein. To characterize that, we introduced some additional local features in addition to those item coordinates, such as the bond angles, the dihedral angles, so on and so forth. And these additional local features can also be calculated in a very fast way, almost with linear computational complexity in real time. So the introduction of these local features does not hurt our model scalability in terms of the number of data samples and the model parameters. And we call this new model VisNet. This model was published in Nature Communications. And if we really test this VisNet on some benchmark, we use that to predict the energy and forces of different proteins, basically with, for example, 200 items and up to tens of thousands of items, very relatively big proteins. VisNet can achieve a significantly better accuracy than classical machine learning false fields. And also, in many cases, the average error from the DFT calculated results is very small within the chemical accuracy error bound. And with this VisNet model, we once again try to test whether it really works well in some real competitions. So we participated in the first global AI drug development competition. And there are over 1,000 teams participated in this competition. And this competition has a very real task. It is to predict the inhibitory activity of small molecules against the main proteins of the SARS-CoV-2 virus. And the other task is, small molecules capability in suppressing the viral replication in CAR-2 cells. So these are two tasks. And we participate in both tasks and all win the first place. And you can see there's a big margin between our results and the second place. Once again, it demonstrates the power of the AI model we developed. And as I mentioned earlier, this paper was published in Nature Communications early this year. And this paper was highlighted by the editors of both AI and machine learning and the editors of biology and methods. So I received quite a lot of attention. Something even more interesting is, so if we have a power to simulate large molecules like proteins, using AI, in a limited time period, you can see those movement of the items, and eventually you will know what's going on in terms of the conformation changes of the proteins. Then what can we obtain on top of that? Can we do some meaningful scientific discovery? Can we know some knowledge that people never know before? So with that in mind, we use our AI models to simulate the dynamics of the spike protein of SARS-CoV-2. And in the spike protein, there are two major components. One is called receptor binding domain, RBD, which is responsible for infecting human cell. And the other part is called NTD, N-terminal domain. Before our research, people know nothing about it because it does not really bind with the ACE2 receptor of the human cell, but it's still there. We do now have no knowledge about why this virus spike protein has a component there. And after we use our AI model to do the molecular dynamic simulation, we found some very interesting phenomena. So basically, we found this NTD part also has a key function in changing the conformation of the whole spike protein. Basically, it works like a wedge. It wedge in and wedge out. When it wedge in, sometimes it will change the positioning of this RBD. If the RBD is really in an upper position, the virus has a very strong infectivity. It will bind with the ACE2 receptor of the human cell. But if in some other cases, when this entity move around and the RBD will fall down, in that case, we call that a closed conformation and the virus has no infectivity to human cell. Then that really gave us some really hints. The previous unknown part, entity, could also serve as an effective target for us to deal with the virus. For example, if we can discover a small compound to change the NTD's movement, and therefore to change the conformation of the RBD, and therefore change the effectivity of the virus, then we can get the virus, get this disease cured. We published that result in an international journal called Advanced Theory and Simulation. And because this is the first time that people know the function of NTD based on molecular dynamic simulation, it received quite a lot of attention, and it was published as a cover page article. Okay, so that's the story about how we use AI models to help molecular simulation. Given a molecule, we want to know what's happening over there. But I have to say, only having the capability of simulating the dynamics of the molecule is not enough. Sometimes we want to know more. I will give you two examples later on. But first of all, let me tell you why simulation is not enough. So first of all, even if we have the AI model, we can do some simulation in a very fast way, much faster way than the previous simulation tools. It can still only simulate a relatively short period of time. For example, like a PS, those small period of time. But for many biological phenomena, we need to have a long trajectory of like milliseconds or even seconds to observe some really meaningful biological behaviors. That will take a very large of a computational resources to achieve that, and still we need to maybe wait for hundreds of years. And second, this molecular dynamic simulation is a Markov process. Each time, each step, it can only have a very minor movement. And so if the energy surface of the molecule has a very complex landscape, and for some parts there is a high energy barrier, the molecular dynamic simulation will never help us to overcome that, to sample some particular conformations. And the last one is, molecular dynamic simulation can only be done for a given, a known molecule. If we want to really design some unknown molecule, a totally new one, if we ask a molecular dynamic simulation to say, can you give me a candidate to cure a drug, a new molecule, we never see it before. We don't know how to do with that, because molecular dynamic simulation can only be done if we know all the items and know their initial positions. With those in mind, in the past year, my team has done two pieces of very interesting research. The first one is called the Distributional Graphormer, which is still deal with a given molecule. But it is not just to do molecular dynamic simulation, it wants to get the whole landscape of the, for example, energy surface of the molecule in an end-to-end manner. So without doing those Markov chain simulation, we get the overall distribution immediately. So we will know the global footprint, and we can do more effective sampling of those conformations behind a high energy barrier. The second one is called TamGen. It is a conditional generation model. Given some properties, this model can directly output a new molecule, which you have never seen before. So let me introduce them one by one. The first one, which is, I think, very interesting, but in order to explain that well, let me tell the story about the protein structure prediction first. I think this is a very hot topic. Many people in the audience must know about that. AlphaFold, AlphaFold 2, and recently AlphaFold 3. The underlying problems these AI models are solving is to predict the 3D structure of a protein given its sequence representation. And this is a big challenge, and people usually say this is a 50-year challenge. And people see some hope after AlphaFold was published in 2021. And also this year, AlphaFold 3 extend that capability from protein to complex and biomolecular interactions. But we want to ask the question, given these lines of research, is this structural biology problem really solved? Are there still many big gaps left for us to further deal with? The reality is that protein structure prediction is far from enough for us to understand the whole biological knowledge. Maybe many of you have heard this sentence. In biology, structure determines function. So this is why people have put a lot of efforts on predicting the structure of the proteins based on the sequence information. But I have to say, this is a common misunderstanding. Because the fact is not structure determines function. The fact is that the structural dynamics determines the function. It is the change of the structure. It is the distribution of the structure really determines the macroscopic property of the biological system. Let me give you one example. This is a specific protein, which is a human BRAF kinase. It is a target for the therapy of non-small cell lung cancer. And according to some experiments, we know for this protein, there are two typical conformations. One is called on-state conformation, like this. The other one is off-state conformation, just like this. And it is the transition between these two conformations determines the biological function of this protein. But if we give the sequence of this protein into AlphaFold, what it will output, it is this one in orange. Basically, this is the average state of these two real conformations. And in reality, this conformation almost never occurs. It is not the fault of AlphaFold, because AlphaFold was trained to predict static single structure. And when some protein have multiple structures, it can only predict one of them or the average of them. That's very easy to understand. But if you can only predict the non-physical, non-existing average state of this protein, we actually know nothing about its biological function. This is a real, distribution of the conformations for this protein. There are two very typical states, but there are also some other states in between, but with relatively higher energy and lower probability. So if we can only have the capability to predict a single static structure, we will know nothing about the whole landscape. The hope is that we can have a predictor which can directly output the equilibrium distribution of the entire conformation space. Then we will know everything about the macroscopic properties of the protein. So this is just the design goal of the distributional graphormer. We want to start from the sequence distribution of a protein, using this model to directly predict the overall landscape of the conformation space. How to do that? So basically, this is a diagram of the distributional graphormer. It contains two key components. The first component is really to understand this protein. Because protein is complex, and its distribution will also be complex, you need to have a very powerful model to understand the deep knowledge inside the protein. And we leverage Graphormer, because previously we have already introduced Graphormer has a very strong power in model molecules. And the second part is, based on the understanding of the molecule, the protein, we want to generate the distribution, the equilibrium distribution of it. And how to generate or sample from the distribution? A very natural choice is to use diffusion model. Diffusion model has the power to generate or sample something according to a given distribution. And I have already introduced Graphormer before, so here I use one more slide to introduce the diffusion model we used in distributional Graphormer. I think many people in the audience may have been very familiar with diffusion model already. So diffusion model basically starts from a specifically designed, starts from a complex distribution, and gradually, step by step, add noises, eventually to achieve a simple distribution. And then we can use a reverse process to start from this simple distribution and eventually achieve that complex distribution. There is something unknown inside this reverse process labeled in red, which we usually call the skull model. So if we can use a AM model to predict this skull model based on the, these molecular representations, And then we will get the detailed specification of this reverse process, and then we can do sampling and do the, according to the complex distribution. This is the job of Graphormer. If a Graphormer can do this prediction and generate the score model, we can use the diffusion model to sample different conformations. It looks very natural and straightforward, but basically when we really want to do it, it has a lot of challenges. The first thing is the data scarcity. For molecular dynamics simulation of different conformations, we have very rare data. You can understand, for each molecule, we use a very expensive chrome EM to get the structure of it. And usually, through those wet lab experiments, you can only get a very small number, if not one specific structure of it. So for most of the public data set, each protein does not have many structures, only have one or two. How can we use that to generate the whole distribution landscape? That's one challenge. The other one is, to train a diffusion model, you need to have the step-by-step supervision. And sometimes we only have the endpoint supervision signal. How we can really link that together? So to solve that problem, we, in addition to the traditional supervision labeled part, we introduce a self-supervised signal loss function to guide the training process of our diffusion model. It is based on the Fokker-Planck equation, which is actually the underlying equation of the diffusion process. It can ensure that when we train this diffusion model, step by step, it can have some consistency over time, so that it can regularize the whole process and also propagate the endpoint supervision signal throughout the whole diffusion process. In certain extent, it serves as a pre-training purpose. Because we do not have many real data, labeled data, we use this kind of pre-training or regularization technology to ensure we can still get a meaningful model trained. Okay, so let's see how this distributional Graphormer performs. This is the first experiment. We obtained a very interesting data set, which is regarding the SARS-CoV-2 main protease. There's a kind of organization called Folding at Home. Many individuals, they contribute their computers' power to this project to really generate some molecular dynamic simulation results. It's a huge project. Eventually, for this main protease, people have already obtained 2.6 milliseconds long trajectory. It's very long. You can already see many conformation changes inside. And that consumes 26K GPU days overall, contributed from many other people, many individuals. And this purple curves here are basically the visualization in the 2D dimensional space based on the simulation data from Folding at Home. And then we use a distribution Graphormer to sample for this protein. And the orange points are the samples generated by the distribution Graphormer. And you can see we only sampled 40K structures using 18 GPU days. So that's kind of thousands of times of acceleration as compared to the Folding at Home. But if you look at the distribution of the samples we obtained with the ones, the purple curve obtained from Folding at Home, they actually match very well. In certain sense, it demonstrates the efficiency of the distributional Graphormer. And the second experiment is also very interesting. We have tested many proteins. These are 4 typical examples. Those proteins have 2 or more typical conformations. For example, this one has a blue conformation and an orange conformation. And this, semi-transparent cylinder are the ground truth conformation obtained from those Cro-EM experiments. And those very thin pipeline are the structure predicted by the distributional Graphormer. You can see we actually matched very well with all those multiple conformations, very accurately. But if we use AlphaFold 2 to predict these structures, you will find something very interesting. For these 2 proteins, AlphaFold 2 can only predict the average states, which never exist in reality. For this one, AlphaFold 2 can predict the blue one, cannot predict the orange one. But if you add some perturbation, some random perturbation to the AlphaFold model, eventually it will generate that orange one. And for the last one here, no matter how you perturb the AlphaFold model, it will never generate the orange one. So that's the demonstration of the capability of AlphaFold versus distributional graphormer. The third showcase is also very interesting. So because the transition between different conformations really determines the biological function of proteins. So can we really predict or simulate the conformation transitions? What is a pathway? Previously, in the field of structural biology, people usually use some linear interpolation to do this, structure pathway simulation. The problem is that you can always get a very good animation in that way, but the points in that pathway might not be physical at all. Many of the points are just artificial. Distributional graphormer has a good capability in producing very physical pathway because it has a hidden representation. It's not really in the geometry space. It can do the interpolation in the hidden space. And based on the predicted structure, it can use a diffusion model to generate the real structure. So basically, the diffusion model ensures that all the structure sampled from it will have a low energy. That is very physical in the world. That's some experiments to results for distributional graphormer. This work was published in Nature Machine Intelligence on the same day when AlphaFold 3 was published. That's quite interesting. We are doing some collaboration with some professors in the US to use this distributional graphormer to predict some new conformations of some very important proteins. I will not really tell you the details, but for that protein, the conformation was never observed before, but distributional graphormer predict that. And then that experimental group used their Pro-EM devices, identified that the predicted structure really exists with a very large probability. So we are really doing some really interesting thing. If that can be eventually verified, it demonstrates the power of the AI tools. We're not just analyzing existing data to really compete on some benchmark evaluation. We can discover new things. That's something we're doing today. Okay, this is the last example, last model I will introduce, which is TamGen. The design purpose of TamGen is not to really simulate or sample from an existing molecule. It is to generate a new molecule given some properties we specified. And to tell this TamGen story, let's have a look at the drug discovery pipeline. I think many of you may also be familiar with this. Drug discovery is a decade challenge, which will usually cost billions of dollars. So this is a 10-10 problem. Over 10 years, over $10 billion to obtain an effective drug. And you can see there are many phases, many steps in the drug discovery pipeline, and each of them will consume multiple years. Even if we leave aside those clinical trials like phase 1, phase 2, we just look at something that computational methods can help. For example, targeted discovery, the high throughput screening, hit discovery, or lead compound optimization. All those things still consume more than 5 years. Then the question is whether AI can help to speed that up. If we can compress that 5-year journey into, for example, 1 week, then some magic will happen. So that's the purpose of AI-based drug discovery. But why this drug discovery pipeline is so long, so costly? Let's have a closer look at it. So basically, given a target, usually we will go through a very large compound database, one by one, to see whether they have the potential to bind with this target. This is what we call virtual screening, high throughput virtual screening. We have many tools like binding affinity prediction or docking tools, which can be used in this process. But this process is slow because usually the compound database is very, very large, like 30 38 billion compounds in one database. So if we go through the database, call those tools each time, it will usually take, for example, half a year or even 1 year to get some meaningful results. But on the other hand, even if the database is very large, with tens of billion compounds inside, it is actually very small as compared to the whole chemical space. Because this is just a screening of some known compounds in our human history. But the whole chemical space is much, much larger, you can see, maybe 10 to the 60. And someone even estimate that to 10 to the 180, something. So very huge chemical space. Then, can we avoid this high-throughput screening paradigm? Can we use a generative AI model to directly output a candidate for the drug? Actually, many people have been doing that. And a typical way is to directly generate molecules in the 3D space. There's a good reason of doing that, because the molecules need to bind with the target. Target is a protein. The binding is determined by the 3D space, because in the protein there's a pocket, and if we can generate the molecule with a specific 3D structure, if it can really fit well into the pocket, we have a high binding affinity. This is why most of the works, they generate new molecules in the 3D space. But unfortunately, in this way, they can achieve a very good binding affinity. But if you look at all the molecules they generated, basically they are not real. We don't even know what they are. They have many, you can see the large rings or the cascading small rings. And if you ask a chemist to look at those molecules, they will say, it is almost impossible to synthesize any of them. That's the challenge. To solve this challenge, in TamGen, we use a very different way. We generate the molecule in 1D space, not in the 3D space. So we train a chemical language model, just like GPT, based on all the smells sequences of the molecules we know, those tens of billion compounds. And then this model ensures that for anything it generates, it will be very, very natural. It will have a very high probability to be synthesized. And then how can we deal with those structure information? We use an attention mechanism to fully leverage the 3D structure of the protein target, use that as an input condition to our generation model. So we also leverage the structure of the protein very well. And the third one, we also have a variational encoder. I actually have some animation. We also have a VAE, the variational autoencoder part, which is to deal with the one-to-many mapping. Because for each protein pocket, you can have many different kind of compounds, all band with it very well. So we use a VAE framework to deal with that one-to-many mapping. With this, this is the compound we generated. Look at them. Looks quite natural. And we also work with a partner who has strong wet lab experimental capability. They synthesize those compounds very easily and test those compounds in some real scenarios and really effective. So this collaborator is Gidi. I guess some of you may have heard of that. Gidi was established by the Tsinghua University and also Beijing government and the Gates Foundation. The three organizations co-founded this Gidi, which is called the Global Health and Drug Discovery Institute. And we collaborated with Gidi, gave them the compound we generated for the targeted disease they care, like the TB, 肺结核, and the SARS-CoV-2. And then they synthesized those compounds and conducted some experiments, like the cell experiments and the enzyme inhibition experiments. And the results are just surprising. For this coronavirus, our generated compounds, we actually gave them five, then synthesized some of them, test one of them. It achieved almost 10 times improvement over the best known lead compound in the history. In terms of the IC50, this is an enzyme inhibition indicator. And for the TB, scenario is different. They have a reference compound, and they ask our model to optimize over that. And we give this into our model and generate a new compound which has over 100 times improvement in terms of IC50 for that compound. So all those results are just so surprising. And previously, Giri and other collaborators, they never thought AEI can make such a huge difference. So based on these great results, we have established some additional collaboration, and Gates Foundation also sponsored us using $1 million to sponsor my small team to conduct more research on the AEI for drug discovery. I think we can skip this slide. It's just a comparison between those simulation-based screening methods and the end-to-end generation methods. They really have a very different behaviors. And what's interesting is this story, simulation versus generation, does not only apply to the biology or drug discovery space. In material space, we observed a very similar thing. In Microsoft Research AI for Science, we have recently published 2 papers. One is called MetaSim, the other one is called MetaGen. MetaSim is just to AI model just like Graphormer to predict those material properties very well, very accurately, almost a chemical accuracy. And MetaGen is just like TamGen. If given a property, it will generate a material directly. And these 2 models can form a flywheel, help each other. And I think Dr. Tian Xie, who is an important author of both papers, will give a talk later today. He is also a kind of award winner for the Frontier Award on the opening ceremony. So if you have interest, you can go to that talk, talk to Dr. Xie to understand more about these works. Okay, so up to here, I have introduced the technical part of my talk, and I will use the last few slides to introduce the organization I'm currently in. This is called Microsoft Research AI for Science. I think many people have heard about Microsoft Research because we have been an organization with over 30 years of history. But Microsoft Research is a fundamental research lab who actually actively seeking evolution, even reform into itself. So just 2 years ago, we did an experiment, established a new lab inside Microsoft Research, which we call AI for Science. This is a mission-driven lab. This is not really a fundamental research lab. It wants to have a very clear goal to use AI to disrupt scientific discovery. And the research work I have introduced in this talk pretty much come from this new organization done in the past 2 years. We have a global team. As you can see, we have people from Beijing, from Shanghai, from Cambridge, from Berlin, from Amsterdam, and US, Redmond. So this is a very international team. Those team members collaborate very closely together, just in one project, on the same document, same paper, same code base. It's a new experiments, very interesting. And this is basically how we view the world, how we do our research in AI for Science. We have AI core. Basically, that's the invention of the basic AI models like Graphormer. And in the middle, we have these intelligent computational tools. That is based on those AI models, how we can do the simulation, do the sampling for a molecule. And the outer circle is grand scientific challenge. So if we have that capability, how can we deal with some really challenging scientific tasks like drug discovery, like material discovery, like climate change, so on and so forth. So basically, we hope with AI, with the efforts of this organization, we can really make the world different. And if you have an interest, have the same dream, you are highly welcome to join us. Yeah, so that's all for my talk. Thank you very much. If you have questions, I will be happy to take.
Thanks for a wonderful talk. So questions?
Thanks for the nice talk. I wonder if it's possible to predict new high temperature superconducting materials using generative AI.
Can you repeat it?
I
Predict what material?
High temperature superconducting materials.
Okay. Yeah, that's a grand challenge. And basically, to be honest, this is a dream of many material scientists. So we can predict the temperature, the room temperature, superconductivity material. I think the challenge is as follows. For example, you need to have a very good simulation or prediction model to understand the behavior of the material with respect to the pressure and temperature. And how to train that model is non-trivial, because in most cases, if you use some quantum chemistry tools like DFT to calculate some properties for material, you are actually calculating the ground state information, maybe just at normal pressure and normal temperature. But when we really want to synthesize a material, even if the material eventually you synthesize will work in room temperature, in the normal pressure, but the synthesization process will really go through a very large range of temperature and pressure. So we need to have a very good model to work beyond the world we are living in. High temperature, we need to know about that. And that is exactly the purpose, the goal of one of the work I mentioned earlier, the MetaSim work from our organization. I encourage you to take a look at the paper, very interesting. It can predict the energy, force, and other properties of a material at any given temperature and pressure. So hopefully, we believe that MetaSim has a potential to help us identify something like superconductivity material. But that's still a long story. Usually, AI for science will have this challenge. We can do many things in a computer, using computer to all the simulation. But when we move on to the real-world synthesis and the real-world experiments, there are many, many new things we do not know. We even do not know. One typical example is, even if you generate a material, who can synthesize that? With what kind of purity you can really achieve that? In the history of material science, there are some examples that people already know one material for decades, but no one can really synthesize that and use it. After one very capable professor invented a new synthesization process, make that done, and win a Nobel Prize, something like that. It would take decades to achieve that. So that's a typical gap between theoretical or experimental or computational results with reality. But I hope that with AI, with more the collaboration between different parties, that gap can be reduced, but still not easy.
Very nice talk, thank you. In the self-attention, so you calculate the correlation between the objects, right? Do you consider the direction of correlation? So, for example, the causal relationship among objects, and consider the size and sign, positive or negative, and stress of correlation. So, do you consider that?
Yeah. So in a typical attention mechanism or transformer, there's no such consideration directly, but somehow we can build something into the node or object features. So basically, basically that's also the positional encoding related thing. You can have bias, you can have all those positional encoding into a node to describe this property. For example, even two words, like in natural language case, if two words are exactly the same, they're the same words, but we can assign a different positional encoding to indicate different positions. Also in molecules, even two items or two fragments are identical, but you can introduce some additional bias into that, so that the whole graph will become some kind of a symmetry, and not a kind of symmetric process. It's doable.
Yeah, that's good. Other question. Can you consider high order interaction? Just like one node influence the connection between other nodes.
At this moment, not yet.
So
Yeah.
you will be interested because high order interaction is quite universal in nature.
Currently, for example, for the transformer for the tension mechanism, it only have those kind of pairwise relationship.
Yes. Okay.
But this is a kind of global pairwise. Every pair will have a chance. But what you mentioned, using the high order thing, one intervene the region between the other two. I think there are some research like high order attention in the not really in the molecular space, but in some other places. But once you do that, the computational complexity will increase dramatically, and how to deal with big system will remain a new challenge.
Okay, good. Thank you so much.
Thank you.
In the material science, do you consider the electron spring interaction?
For that particular paper, first of all, I'm not a co-author, so I don't really know every details of the MetaCM and MetaGen work. I encourage you to talk to the real author. We will give a talk this afternoon. Well, not really in this room, but you can check the schedule.
Thank you for the talk. That was great. I'm Michael Martinez, and I'm doing my PhD in computational mechanics, and we're using AI. So this topic is very close to it, and we're also working with graph neural networks. So to make a comparison, maybe with more, let's say, a normal size objects like a crash of a car, right? When you use graph form and you give the input, are you actually inputting the whole molecule like a whole text, and then you're getting the output of that one on the next step to predict the dynamics, and you do that recursively? Or how do you actually get to all those like snapshots, like the evolution on time? Is it like a forward like integrator, or do you actually input it and just analyze it? So how much history do you actually use for training of the whole sequence?
There are several steps. For the Graphormer, for example, it is not a molecular dynamic simulation model. It is just a molecular property prediction model. So we train Graphormer, we just give the energy, force, and other properties for a static molecule as the training data. So there's no dynamic thing when train the Graphormer model. But once this Graphormer model can predict the energy very accurately, we leverage that to predict the force and then change the atom position and run this simulation process. So in other words, Graphormer is not a molecular dynamic simulator, but it is a key component of a molecular dynamic simulation process. Yeah, another interesting thing related to your question is, when we really do this simulation, like a molecular dynamic simulation, we need to really have a whole system, just like you mentioned. But the reality is that, for example, if we have a protein, we put it into some water. Like, if we have a water box containing that protein, the whole system will be so huge, maybe billion items inside. Then, for most of the models we have today, they will encounter a huge challenge. For Graphormer, we can only handle molecules with, for example, hundreds or thousands of items inside. Using VisNet, fragmentation technology, we can go 1 or 2 order of magnitude, but still, that's less than 1 million. If we have a water box with a billion items, I don't think anyone can do that with that accuracy. People have to do some, multi-skills modeling. For some part, maybe using classical force field. For some critical parts, using the AI models like this. So that's the way people are handling those large systems.
Because the previous models that you mentioned, like graph networks, basic ones, those are usually nodal based. So you have one node, neighbors, and you output the node, and through message passing, you just upgrade the whole graph. And those sort of techniques, you just rejected them and just stick to transformers and the whole graph, or are you actually also considering to get into that? Because that will give you some sort of a shape agnostic situation, because you can work with 5 nodes or 1,000 nodes, but the problem would be the message passing, right?
Actually, I think that's a very interesting question, and I don't really have a good answer for that. First of all, intuitively, I also think a graph is a very good way to model those, object interactions like molecule. And even for very large models, you can have a hierarchical representation of graph. You can have some local, global, short range, long range trade-off. So you have many tricks to handle that. But on the other hand, models like a Graphormer, which is a global attention, it is not a local, connection. It will suffer from, if you have a big system, you cannot really deal with that using a kind of trade-off. So on the one hand, I agree with you. I will also like a graph very well. But on the other hand, the recent advance of AI really indicated that the scaling law matter a lot. And the transformer, or also Graphormer and also related models, can easily benefit from that. So this is why, as I show, we can easily scale to 20 billion parameters and really achieve the SOTA for all the benchmark evaluations. But for graph neural networks, it is not the case. People haven't really obtained enough evidence say I can easily scale up to hundreds of billion parameters and beat everyone. So it is beautiful, it is reasonable, but in terms of accuracy and some practical consideration, we have to go the other direction. In the future, hopefully, someone will really invent a new category of models which can have both very nice intuition and also scalability. So let's see, we will do that.
That would be great to see it. Thank you.
Thank you very much. Yeah, already over time.
Yeah,
10 minutes.
already over time. So if you have more questions, you can ask Professor Liu later. Yeah.
Thank you.